Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the idea of union of events and the use of addition rule. So here we've got A and B as two events that are defined in a sample space. And when you talk about the union of events A and B, then you are essentially talking about having all the outcomes that belong either to A or to B or to both A and B. So in other words, we are talking about outcome that belongs either to A, so just A, this area basically, this is just A, or just B, so B is just this area, or we can also talk about them being in both A and B, so this middle area where we've got the intersection between two sets. And when we talk about the notation used, it will be the word or this symbol. So this is the union symbol, okay? Now, in order to find the probability of the union between A and B, you can use this formula. And this is the simplest formula when you have two events, A and B. So here we've got the probability of A plus probability of B minus the probability of the intersection between A and B. And this result here will give the answer to probability of the union of two sets, A or B. And next, we are going to look at the reason, more or less the intuition behind the formation of this formula, like how this formula comes about. So if we talk about probability of A, okay, so I'm just going to sketch the area related to finding probability of A. Basically, when you talk about probability of A, you're talking about this whole area, the whole thing about A. Of course, this is also included because this is also in A, yes? So that is probability of A. Next, if we talk about probability of B, the area associated with that is going to be this area, everything related to B, which also include this part here because this is also belongs to B. Okay, so this is the area related to B, and I hope you can see that around this area, this particular intersection area, it has been double counted. So you can see there are the green lines and the blue lines around here. So this area has been double counted. So there has been in the process of trying to find probability A and probability B, this small area here at the intersection part has been double counted, and this is wrong, and for that reason we have to make sure that we minus the probability on the intersection area. So we're going to minus one layer of those lines. So if you minus that, let's say you minus one area, so you will minus PA intersect with B, just this spot, and now the area looks alright because every section, for example this section, there's only one set of lines, okay, so it has been counted once only, and this section also there has been one set of lines, the blue line, so it has been counted once, and this part is also the same, we have one set of green lines. So the area has been covered properly, and there is no like double counting or whatsoever, and for that reason, again, intuitively speaking, that is why the probability of A or B is given by this formula here. So we start by finding what's probability of A plus what's the probability of B, and then we've got to minus the intersection area because, like I have demonstrated to you just now, the intersection area here has been double counted, and that is wrong. Okay, naturally the previous idea can be extended when you have 3 events. So let's say you want to find the probability of A union B or union C. So naturally the formula gets extended, and we have a longer result here on the right hand side of the equation. So you can see that we have probability of A plus probability of B plus probability of C, and we've got to minus sum of the intersection area given here, and then we've got to plus another intersection area. Okay, and I'm just going to demonstrate to you how intuitively this idea here makes sense by sketching the area. Okay. So if we talk about probability of A, so this is the area of finding probability of A. Okay, so we are talking about all this area. Okay, you can see that this whole thing here is A. Next, let's talk about probability of B. So probability of B is this area. So included in this part. Also in this part, yes. And this part. So you can see that some areas have been double counted. Okay, this area. And bear in mind that therefore we need to somehow minus this intersection area later on. Okay. Next, probability of C, which is C is this whole round circle of set, and maybe it looks like this. Okay. Yeah. Okay, so we can see that we need to do some adjustment. We need to minus some of the intersection area, because you can see, for example, this area here has been double counted. This one is also double counted. This is double counted, and in the middle here is triple counted. You can see the lines of green, purple, and blue all together in this small region. So now we're going to start erasing some part. For example, we're going to erase one part of A intersect with B. So A intersect with B is this area. So we're going to remove one layer from that area. So let's say we remove this one. Okay, so we remove one layer. This is also one layer in this area. So there we go, we are done with this part. Okay, we have removed that. Next, we're going to remove another layer from A intersect with C. So A intersect with C is this part. Okay, so we are going to remove another layer. All right, so let's say we remove one layer carefully. So remove one layer from this part, remove one layer from that part, and another layer. So there you go. So we've done this part. Now let's remove another layer from B intersect with C. So B intersect with C is actually all this area. So we're going to remove one layer that we have like double and triple counted just now. So we're going to remove this one layer in this area. And we start off by this one. You remove one layer, you remove one layer. In this area, we're going to remove another layer. Let's say we remove the green layer. Doesn't matter really, green or purple. So let's say I remove another layer in this part. And you can see that by doing the process of removing one layer in the intersection area, we have come to this image here, where I hope you can see that now this area has ended up not being counted, because in the process of removing all these layers, we have somehow eliminated this part here, and for that reason we need to add the area where there is intersection between set A, B and C. So we're going to add this area, and there you go. So now we have every region covered with covered properly. You can see that, for example, this region has been covered with one line, blue lines. This one also been covered properly. This area also has been covered. This one, that one, and finally this one over here. Okay, so basically that's the intuitive idea on why the formula for the union of set A, B and C is given as such. So in order to find the probability of these three events, this is the formula that you have to consider. Okay, all right, now we're going to look at this example here. This is a very simple example of finding the union of two events. Here, a vice chancellor of a university has proposed that all students must take a course in ethics as a requirement for graduation. And here is the two-way classification table and the responses of these faculty members and students. So here we've got faculty members and students, the rows, and the columns here are basically their reaction, whether they in favor of the proposal or against the proposal, or being neutral about the proposal. And the question is asking you to find the probability that one person selected at random is a faculty member or in favor of the proposal. You can see clearly that in this example here, there is an intersection area between faculty member and those that are in favor. So this is the intersection area. We've got some faculty members that are also in favor of the proposal, and therefore in order to find the probability of a random person being a faculty member or in favor, then we have to apply this very simple formula which you have already seen. We have to minus the intersection. Okay, and in this case what we have is we want to find the probability the person is a faculty member union with the fact that he is in favor of the idea. So probability that person is a faculty member is going to be the total number of them being faculty members, so 70 over 300. So that is the first part. Next, the probability of the person is in favor. In favor is this part. So the number of people in favor is 135 over 300. And finally, we got to minus the intersection part, which is going to be 45 over 300. Okay, and you will get that the answer to this one is 160 over 300, and this is approximately, or if you use 4 decimal places, the answer is going to be 0.5333. Okay, all right, now let's look at this question here. Suppose there are two events, A and B, with the probability of A occurring is 57% and B occurring at 20%. So choose the correct answer to the chance that either A or B are occurring. So is it A, B, C or D? So this is the multiple choice question, and maybe this is the part where you want to pause the video for a while and try to answer this question on your own. And then later on, you can compare your answer with mine, okay? Right, so we want to know what's the probability of A or B occurring. Well, you can see that first of all, the formula for A union B is BA plus BB minus the intersection of A and B. This is the case when the events are not mutually exclusive. So when the events are not mutually exclusive, there will be some sort of intersection area in the middle here for A and B. Okay, so in this case, the result for this one is going to be 57% plus 20% plus something else that you don't know. Okay, so it doesn't matter. So here we can assume that the result is about 77% minus some value. So that is the first situation that you might consider when the events are not mutually exclusive. There's also another possibility where the events are mutually exclusive. So when the events are mutually exclusive, there is no intersection here because the sets are properly separated. And in this case, probability of A union B is going to be equal to PA plus PB. And the intersection here is going to be just 0. There is no intersection. And in this case, we will have 57% plus 20%, and that is equal to 77%. So these two situations have to be considered, and you'll see that the answer to this question here is going to be at most 77%. That means the probability of A or B occurring, it could be 77% if you consider the case of mutually exclusive, and it can be less than 77%, and therefore the answer is at most 77% because it can be the highest value is 77%, but it can go lower than that if you consider the events where A and B are not mutually exclusive. Okay, now let's look at this example here. Consider having two events A and B, and suppose that every outcome in sample space S has probability greater than 0. So here probability of A is 57%, probability of B is 73%, and the intersection of that is 57%. So construct a Venn diagram to depict the above statement. And this is also the part where you can pause the video for a while, try to do it on your own, and then perhaps after that you can compare your answer with mine. Okay, let's assume you have done just that. Now, this is how the Venn diagram is going to look like. So first, this is the sample space. And you can see clearly that probability of B is bigger than probability of A, 73%. This one is 57%. And the intersection of A and B is 57%, which is equal to this probability here, probability A. Therefore, you can imagine that set B is going to be looking like this. So this is set B, where the probability is greater, 73%. And set A is going to be inside set B, where the probability of that occurring is 57%. And you can see that this area is also the intersection area between A and B. So the intersection area here, 57%, is equal to the probability of A. So this is how the Venn diagram is going to look like. Okay, I think that's all for now. Thank you very much for watching.